These two are the equations that we derived last time, and the first one, this one here, is also called the radial Schrodinger equation. Why is it radial? Well, because the function phi depends on r. It only depends on r, which is the radial distance from the center of the nucleus of the electron, let's say. It represents the position of the electron measured from the center of the nucleus, which is almost coincident with the center of mass of the system. For the considerations that we made in the first part of this of this course. Whereas the second equation is an eigenvalue equation for the operator L squared. Now let me explain what I mean by L squared. L is an operator. Maybe I could call it L hat to denote that it is, to stress the fact that it is an operator, but it doesn't really matter. I mean, by L I mean an operator. This is the operator of angular momentum. And in quantum physics, it is easily derived from classical mechanics as well. So it can be extended from the definition of classical mechanics, because L, which is the angular momentum if we have a particle, so it's the angular momentum of the electron. So we have to consider consider a cross product between the position vector, which in this case it's r. It is the distance from the center of the nucleus, cross with the momentum operator, where the momentum operator is equal to minus I h bar gradient. And now if we go to spherical coordinates, or if you want you can call them polar coordinates, and you write the expression for L squared from here, you can find that this quantity here above that I'm circling in red is exactly L squared. It is exactly the square of the angular momentum, and that is important. It is very important to realize, which means that this quantity here on the right is the eigenvalue of the angular momentum squared. Okay, and one can calculate, one can dig deeper into this equation and find the solution, and one can find the solution for this function y, and the solutions in general, because there are multiple solutions, are also called the spherical harmonics. Okay, but it is not something that we are going to do here because the main purpose of the course is to find the discrete values of the energy. And this equation here is not going to tell us something about the discrete values of the energy. It is going to tell us something about the discrete values of the angular momentum. But what we really want to solve and try to analyze with better detail is this equation here, is the radial Schrodinger equation. So this is the target of the course. So we want to dig deeper into this equation, but we are not going to solve this equation, at least for now. Maybe in a subsequent part of the course, but it is still not sure that I will do that. I may also try to solve this one, but this course as its main purpose that to find the discrete values of the energy, and I will have to address this equation here. So it's the radial Schrodinger equation. And in order to try to find a solution of the equation, I will have to define another function chi of r, which I will define like this. It is just r times phi of r. So it will be convenient to try to find a solution in this form. Chi of r equal to r times phi of r, or if you want phi of r is equal to chi of r divided by r, and I have to substitute this expression there in the radial Schrodinger equation. Now from here you see that from this this is a definition, okay? You can take this as a definition. From this definition you can see that since phi of 0 should be finite, you can see from here that chi of 0 should be equal to 0, because when r goes to 0 here you have something divided by 0, and of course if you want to get a finite result you have to impose that you have to impose this condition: chi of 0 should be equal to 0. Okay, and we will try to remember this condition, because maybe I mean in the following videos it will be useful, and actually I will use it, so it can be useful to try and remember this expression. But now what I want to do is I want to substitute this expression, as I said, there. Okay, so I have to calculate the second derivative of the function phi and also its first derivative, right? Because you can see that here, let me do it in blue, you have some derivatives of the function phi. So we have to calculate, so let me do it here. d over dr of r squared d phi over dr can also be written like this. Maybe let me also multiply by 1 over r squared, which is here. This is equal to the second derivative with respect to r of phi, because this operator here first acts on this one, and then you have r squared over r squared, which gives you 1, and then you have plus 1 plus 2 divided by r d phi over dr. So this is the result of that. So we have to calculate the second derivative and also this first derivative, but we have to substitute this expression here. Okay, so let me do it down below. It is a simple exercise, but I will do it. D phi over dr is equal to minus 1 over r squared times chi plus 1 over r d chi over dr. Now let me thicken my lines here. So I'm going to try to make my handwriting more clear. And then I have to calculate d squared phi over dr squared. And of course I have to take the derivative of that expression. So I will have 2 over r cubed chi minus 2 over r squared d chi over dr plus, now I have skipped some steps here, some algebra. It's not very difficult. It's actually very easy to do if you know how to take derivatives. I'm just going to give you the result. It's kind of straightforward to calculate. Plus 1 over r d squared chi over dr squared. Okay, so this term here comes from so first you take the derivative of 1 over r here, and also you take the derivative of chi here, and then you add those two expressions and you will get this. Okay, but it is just a simple exercise. Then we have to use these two expressions there. Okay, and I can substitute what I have just found here here. So I have to add 2 over r d phi over dr to d squared phi over dr squared, and it's a simple simple algebra here. You have 2 over r cubed chi minus 2 over r squared d chi over dr plus 1 over r d squared chi over dr squared, and then you have minus 2 over r cubed chi plus 2 over r squared d chi over dr. And you can see that this term here cancels this one, and this term here cancels this one. So it will simplify quite a lot. So I will be left here with an equation like this. So you can also multiply by r to simplify the expression, and you will be left with d squared chi over d r squared plus, here you have 2 mu over h bar squared z e squared over r plus 2 mu over h bar squared e minus l times l plus 1 divided by r squared times chi equal to 0. So I have replaced this definition here and in the radial Schrodinger equation, and this is what we get, right? And this was our starting point, right? So you can see that I have also divided by some factors here because I got rid of this by multiplying by the inverse of that. So I multiplied also the equation by 2 mu divided by h bar squared, but this is just trivial. Okay, so it's easy to get to this equation here. And now what I want to do is I want to define another variable. So I want to change the variable r, and I want to define a new variable era. Era will be defined like this. So this is a definition. We'll see that this will be useful to clean up the equation a little bit, so to make it a little cleaner and easier to handle. I will define it to be some constant that I will have to define as well. So some constant alpha times r. And this constant is a dimensionless quantity. And I will define it like this. Alpha is defined as 2 times the square root of minus 2 mu e divided by h bar squared. Okay, so I am assuming now that the energy here is less than 0. This is important because this is what will lead us to bound states. Okay, so let's say bound states are due to the sign of the energy. Because if the energy is negative, you can think that the potential attraction between the particles will overcome the kinetic energy of the particle, because if the electron has enough kinetic energy, it can also escape from the atom. Okay, so it can escape the attraction. It can overcome the attraction, and therefore we are going to study the energy less than 0. We'll see that it will lead us to bound states. And this definition here for the parameter alpha is useful, and I will show you why. So in particular, if we want to change the variables, we also have to try to find an expression for the operator d over dr. And it is easy to see by using the chain rule that this is just d era over dr times d over d era. But d era over dr is just alpha. So this is alpha d over d era. Whereas d squared over dr squared will be simply equal to alpha squared d squared over d era squared. Okay, and now if you substitute this expression there, and you also have to substitute the expression for r, which is alpha r, and you also have the expression for r squared. With some algebra, you can find that this is equal to minus 4 2 mu e over h bar squared d squared chi over d era squared plus, here we have 2 mu e divided by h bar squared z e squared divided by e era times alpha plus 2 mu e divided by h bar squared plus 4 2 mu e over h bar squared times L times L plus 1 divided by era squared, and then multiply by chi, and this is equal to 0. Now you can manipulate it a little further, like this. You can write that d squared chi over d era squared minus, here you have 1 over 4 z e squared over e times alpha times 1 over eta plus 1 over 4 plus L times L plus 1 divided by eta squared times chi equal to 0. Now this is just a constant here that I can call lambda. This lambda here is an important parameter because it will tell us, right? At the moment we know nothing about lambda, but it will tell us how the energy is discretized or how the energy is discrete. And lambda is just 1 over 4 z e squared over e times alpha, but alpha is 2 times the square root of minus 2 mu e divided by h bar squared. So this was just the definition of alpha that you see there. And you can rewrite it like, you can rearrange these terms like this: z e squared over h bar square root of minus mu divided by 2e. Okay, so this is the definition for lambda. And now the differential equation for chi becomes like this: d squared chi over d eta squared minus 1 over 4 plus lambda over eta plus L times L plus 1 over eta squared times chi equal to 0. This is the differential equation that we have to solve, to work with. Okay, because from here we will see that we can derive the discrete levels of the energy. But I will start from here next time.